Good day everyone. In this video we are going to discuss the concept of flanged bolt coupling along with some problems related to it. Let us have first the definition of coupling. Coupling is a mechanical element which connects the shaft which is in two halves. It is used to connect segments of circular shafts to make a long shaft since long rigid shafts cannot be easily transported. Shown in the figures below are the actual photo and the 3D diagram of a flanged bolt coupling. As can be seen in the diagram on the right photo, shafts named 1 and 2 consequently, are connected by a flanged bolt coupling. This mechanism uses nuts and bolts which connects two flanges. Furthermore, coupling refers to the pairing of two particular sides of the mechanism. Flanged bolt coupling. A flanged bolt coupling is commonly used between connection of two shafts. It consists of flanges rigidly attached to the ends of the shafts and bolted together. The load in any bolt is given by the equation, P is equal to area of the bolt times the shear stress, and if expanded it would be equal to pi over 4 times diameter squared times the shear stress. In shaft connection called flanged bolt couplings illustrated in the figure below, the torque is transmitted by the shearing force, P, created in the bolts that is assumed to be uniformly distributed. For any number of bolts n, the torque capacity of the coupling is equal to P times R times n, which is also equal to pi over 4 times d squared multiplied by the shear stress times R times n. Where P is the load carried by the bolt, also called shear force, R is the bolt circle's radius, tau is the shear stress, d is the bolt diameter and n is the number of bolts. Another important concept is that, if a coupling has two concentric rows of bolts, the torque capacity is equal to P sub 1 times R sub 1 times n sub 1 plus P sub 2 times R sub 2 times n sub 2. Where P1 and P2 stands for the load carried by the bolts in the outer and inner bolt circle, respectively. R1 and R2 is the bolt circle radius, outer and inner, respectively, and N1 and N2 is the number of bolts in the outer and inner bolts, respectively. For rigid flanges, the shear deformations in the bolts are proportional to their radial distances from the shaft axis. The shearing strains are related by the equation. The shearing strain of flange 1 is equivalent to shearing strain of flange 2, wherein the shearing strain is calculated through dividing the shear deformation in the bolts by the radial distance from the shaft axis. Moving forward, using Hooke's law for shear. From the above equation of shearing strain, we substitute T over G for the shear deformation indicated by gamma. Then we obtain this equation: shear stress over modulus of rigidity of bolt 2 times radius of bolt 2 equal to shear stress over modulus of rigidity of bolt 2 times radius of bolt 2. Then expanding the shear stress tau, we obtain force over area for the shear stress, leaving us this equation. If the bolts on the two circles is equal and if the materials used are the same, the relation can be simplified as, force on the outer concentric circle bolts over its radius from the axis of rotation is equivalent to the force on the inner concentric circle bolts over its radius from the axis of rotation. It is to be noted that similar procedure can be used for 3 or more concentric bolt circles. And now that we have discussed the different concepts about flanged bolt coupling, let us now try to solve problems related to it. Problem number 1. A flanged bolt coupling consists of 8 steel 20 mm diameter bolts spaced evenly around a bolt circle 300 mm in diameter. Determine the torque capacity of the coupling if the allowable shearing stress in the bolts is 40 megapascals. For guidance, a figure is illustrated below. First step is to write all the given data from the problem and determine what is needed or the required answer. So we have N equals 8, R equals 150 mm, D equals 20 mm, and tau equals 40 megapascals. In this case, what we need to find is the torque capacity of the coupling. As mentioned a while ago, torque capacity is simply equal to P shear force times R, radius of the circled bolts from the axis, times N number of bolts. Substitute shear force P to area of the bolt times shear stress tau, giving us the formula, pi over 4 times d squared times shear stress times R times N. Using the derived formula, simply substitute the given values, thus, giving us the torque capacity to be 4,800,000 pi newtonum or 15.08 kilonewton meter. Problem number 2. A flanged bolt coupling consists of 8 10 mm diameter steel bolts on a bolt circle 400 mm in diameter, and 6 10 mm diameter steel bolts on a concentric bolt circle 300 mm in diameter, as shown in the figure below. What torque can be applied without exceeding a shearing stress of 60 MPa in the bolts? Laying out first the given values in the problem. We have N1 equals 8, N2 equals 6, D1 equals 10 mm, D2 equals 10 mm, R1 equals 200 mm, R2 equals 150 mm, and tau equals 60 MPa. So to solve a problem like this, we must first interpret the problem and know what to solve for. In this case, we are asked to find the torque given a restraint of maximum shearing stress. Therefore, we have to find the individual shear force that can be generated given the restraint of maximum shear stress, which is 60 MPa. First, let us determine the shear force on the outer concentric circle of bolts. P sub 1 is equal to area of the bolt times the maximum shear stress. Substituting the necessary values, we acquired 1500 pi newtons for one bolt in the outer circle. Consequently, solving for the shear force in the inner circle by using the simplified formula P1 over R1 equals P2 over R2. Substitute P1 obtained in the outer circle, R1, and R2. We attained P2 equals to 1125 pi newtons. Now that we have the individual shear force for each bolt in the outer and inner circle, we can now compute for the torque capacity, which is given by the formula T equals P1 times R1 times N1 plus P2 times R2 times N2. Substitute the given values, so we get a torque capacity of 3,412,500 pi newton millimeter or 10.72 kilonewton meter. Problem number 3. A torque of 700 pound-feet is to be carried by a flanged bolt coupling that consists of 8 1/2-inch diameter steel bolts on a circle of diameter 12 inches and 6 1/2-inch diameter steel bolts on a circle of diameter 9 inches. Determine the shearing stress in the bolts. So for the first step, we need to write all the given data and determine what is needed. The values we have are torque equals 700 pound-feet, N1 equals 8, N2 equals 6, D1 and D2 equals 0.5 inches, R1 equals 6 inches, and R2 equals 4.5 inches. For this problem, we have two concentric circle of bolts and the requirement is to find the shear stress in the bolts. In this last problem, the solution is to determine first the relationship between the shear stresses of the inner and outer circle bolts. So, P1 over R1 equals P2 over R2, which came from deriving the shear deformation formula and the Hooke's law for shear, and since they have the same material of same area and modulus of rigidity, we are left with this formula. Next is to substitute shear force P to area times shear stress of the bolts. Then we will substitute the given values to the equation. From here, we obtain the relation, shear stress or tau sub 2 is equal to 0.75 tau sub 1. After this, we can now use the formula P1 times R1 times N1 plus P2 times R2 times N2. This will give us the value for shear stress for both inner and outer circle bolts, then substitute the values and use the relationship obtained in step 1 of the solution. Inserting the values, we get 8,400 equals 13.4 tau sub 1. Lastly, after a series of calculation, we now obtain the shear stress in the bolts in the outer circle is 626.87 psi and shear stress in the bolts in the inner circle is 470.15 psi. For more series of problems regarding flanged bolt coupling, attached here is the link for your reference. Hope you learned something. Thanks for listening.